Hello, welcome to the first lecture on classical mechanics. Now, before we actually do anything involving Newton's laws or the interesting things that you can do with Newton's laws, I'd like to start by discussing fundamentally what any sort of classical physical theory is. So, the first thing I'm going to discuss is essentially what you could call the metaclassical theory of physics. The metaclassical theory of physics proposes that if you have a system, and what a system is simply a configuration of some sort. A configuration of quantities and objects which can be physically measured. They can have physically measurable effects of some kind. This could be a system of charged particles, it could be a system of neutral particles with mass so that they can gravitationally interact, or it could be some system of particles which obeys some law of interaction that doesn't actually apply to this physical universe, but is in principle a meaningful theory for some universe obeying some classical set of laws. Now, if you have a system, the first principle of a metaclassical theory is that the space of states, the set, or the configuration of all possible states that a system could be in, has the simplest algebraic structure that any containment, any space can possibly have. It's just a set. So, this you could call the zeroth principle. Zeroth principle, space of all states is a set. That is the simple idea of a set from classical mathematics, that it's just a collection of objects, a well-defined collection of objects, so that you can specifically say whether something is in a set or not in a set. And it obeys the basic ideas of unions and intersections, the union of two sets. If you have two sets, two collections of objects, you can imagine the Venn diagrams, the classical Venn diagrams. The union of these two sets is everything that's in both sets. The union is to say that it's everything that's in all the sets. Everything that's in both sets, or if you have a larger collection of sets, everything that's in every single one of those sets. That's a union. If you have a Venn diagram again, the intersection is the part of the sets that they share in common. That is to say, it's the areas where the sets intersect. It's those points that they share in common. And those are the basic ideas of a set. If in the future I need to go into more specifics about set theory, I will. But I don't perceive that as being necessary for the most part. Now, if you have a set which represents the space of all possible states that a physical system can be in, there are essentially three questions that you'd like answered. Question number one: what space? First question you'd like to know is, what actually is the space? What are the possible states that the system could be in? Fairly obvious that you can't do anything if you don't have that. Now, the second question requires an additional structure. This additional structure is time. The question here is time, discrete or continuous? The question is time a discrete variable or is it a continuous variable? Now, you might ask, we just assumed time. What is time? In classical physics, both Newton's physical theory and Einstein's theories of special and general relativity, time is a parameter. Time is, if you imagine a system that's in a state, it's in that state at some particular time. So you could say that the state of a system is a function of a parameter we're going to call time. And the question is whether or not this parameter is discrete, that is to say, it's equal to the integers. It doesn't have to be the integers, it doesn't have to be the whole numbers, but it is equivalent to them in a set theoretic sense. So it could be, it usually is something like the integers. It could be the rational numbers, it could be the natural numbers. It really doesn't matter. Is it discrete? That is to say, you're in a certain state at this time, and then the very next instant, you're in this state over here. And then you're in, say, this state over here, and then you go back to the original state. And you can imagine something like that. It just cycles through these three states forever. And that is a possible system. Time is the parameter over which the system goes from one state to another. This would be an example of discrete time. Continuous time would be where I could say, what is the state of the system at time t equals 0? Then I could say, what is the state of the system at time t equals 0.001? Then what is the state of the system at 0.001006? I could keep dividing up time into finer and finer jumps, so to speak, such that there really are no jumps. And those are the two possible ways that you could configure time, that you could imagine time being configured. And the basic question is whether or not you're one or the other. A continuous theory of time pretty much applies to all major classical physical models. However, there are models of physics, models of certain physical systems, which obey discrete time. The way that you get discrete time in a classical physical theory is typically to take a theory which really does have continuous time, but then to abstract away the behaviors of the system that you don't care about, so that you only care about certain subsets of the processes that the system obeys. The most common example of this is the theory of classical computation. The state of the microprocessor at any given interval of time you imagine to be a certain element of a set. Now, computers are objects which exist in the physical universe, so in some sense they are objects which obey continuous time. But you're only interested in the binary states. You're not interested in the exact momentum of every particle in here. You're not interested in the exact temperature of this thing. You're only interested in the binary configurations. Is this bit here 1 or 0? Is this bit here 1 or 0? Is this bit here 1 or 0? You're just interested in that generic question. And when you abstract that away, every computer that's properly built, should we say, has a clock. clock over here, and it usually has some interval time of on the order of nanoseconds, on the order of billionths of a second. So every 30 nanoseconds, say, the computer jumps forward in time. And you're only interested at each clock pulse what state the system is in. You're not interested fundamentally in what it's doing in between those times. And so even though there is no such thing as discrete time in the physical universe, at least not at the classical level, and probably not at the quantum level either, no matter what, you're not really interested in the vagaries of time between those discrete pulses. So even though